Among all violent causes of death, the highway accident is the #1 killer in the United States today. More Americans were killed on the highways of this country last year than have been killed in all the years of the Vietnam War. We have learned that well-engineered highways can save lives. On the interstate system, for example, the death rate measured in millions of miles traveled is only about half what it is for the rest of the road network. But even expensive new highways can have built-in death traps. These films were taken on a new circumferential highway around Washington because the roadway was not engineered to be safe in wet weather. This is what happens. This particular stretch of highway has since been redesigned and made safer. Accidents have fallen off dramatically, but we'll be looking here at just a few of the accidents that happened within the course of a 2-day period. The Public Works Committee is concerned with how many other danger spots like this may exist throughout the country. That's the purpose of the hearings we're holding in Washington this week. This should be a safe highway. It's a new highway, but there are several things wrong. The grade is too tight. Here we see the same curve from the opposite direction. This poor fella was so excited that when the car stopped skidding, he drove it into the guardrail. Watch the station wagon. The driver of this station wagon is the mother of 4 children. Luckily, she escaped serious injury. But before the station wagon could be removed, you see another car skids down the same embankment. This road needs an aggregate with skid-resistant qualities. It has since been provided. Watch the Volkswagen. Now keep your eye on this truck. This could have caused a multi-car accident on the lower roadway. Only great good fortune prevented it. The Public Works Committee wants to know how many other spots there are like this in America. Here's another location and another day. He almost gets run into coming around and getting started again. These films were taken by professional investigators of the Public Works Committee of the United States House of Representatives. It's our purpose this week to find out how many other places throughout America have these dangerous death traps. They can be prevented by proper engineering of highways in the first place. They can be identified where they exist, and they must be corrected.
This is the film for Session 12, Roadside Slopes and Ditches. This is a test series that was conducted to determine if a vehicle could safely traverse a rather steep side slope. This particular test was designed to verify the computer model that was used to determine design criteria for side slopes. Notice the vehicle comes onto the slope. This is a 3.5 to 1 side slope, runs to the bottom and up to the top of the back slope, which is approximately 145 feet from the edge of the pavement, and then is brought under control. The basic roadway cross-section is a state highway that had been constructed for at least 20 years at the time the testing was conducted. A grid pattern was mowed on the surface and striped with chalk to identify the path of the vehicle. We're exiting at this time at 60 miles an hour and about 25 degrees onto the roadside slope, and you'll notice the vehicle went out a little further than 145 feet, in this case about 168 feet. The basic problem occurs when the vehicle slaps down on the back slope right there. The tie rod breaks, we lose control of the vehicle, and it runs out into the cotton patch adjacent to the roadway, about 168 feet from the edge of the pavement at that point. So even though we talk about clear zones on 3 to 1 slopes of 100 feet, that's not nearly sufficient to take care of a vehicle that loses control because of a mechanical problem such as was described here. The vehicle in each case was rebuilt and put back on the roadway. The driver for the vehicle is in the trailing truck that you see. It's a joystick driving system. Now we're exiting at 15 degrees and about 60 miles an hour. And notice the vehicle went to the bottom, no tendency to be unstable on the side slope, very basic run out. And these tests are one of the bases for the run out distances that are provided in Table 2-1 in the notes. When we talk about the run out distance for vehicles beside the roadway, these tests were used for verifying those numbers. The exit angle was measured by roughing up the shoulder a little bit and looking at the wheel paths at trajectory as it went across the shoulder. Speeds were controlled by the driver. This time we're trying to exit at 25 degrees, which is terribly difficult to achieve, and again we lose control of the vehicle and it goes out in the cotton patch, this time about 185 feet from the edge of the pavement. Notice again when the vehicle right front wheel slaps down on the front slope, the tie rod is lost and it's out as far as the energy will take the vehicle. But 180 feet is not unusual under that circumstance. The 25-degree exit angle is, however, very difficult to achieve, and for that reason we don't think that that's a particularly critical problem. None of the tests at 15 degrees or less resulted in damage to the front of the vehicle and the loss of control that you have seen in these two high-angle exits. This time we're coming off at about 10 degrees onto the side slope, and the idea was to try to test to see if the vehicle could be redirected on a 3.5 to 1 slope, and would it begin to roll over because of instability. So 1 second after it leaves the roadway, counter steering is initiated right in the middle of the slope. The vehicle goes into a drift and drifts to the bottom of the ditch, did not tend to go back up the slope, and was not unstable in the sense of tending to roll. So pretty good performance from the side slope in this particular instance. None of the ditches that existed along the side slope were taken out or replaced or removed. It's just simply the test situation as it occurred. Here we're talking about a loss of control, but this time for a different reason. About 160 feet again out from the edge of the pavement, but the driver simply lost control of it on the joystick and couldn't handle it. The front end mechanism performed well, but the vehicle took off onto the roadside. But again, there was no tendency to be unstable, to roll over, or create a problem. The older standards call for a 4 to 1 or steeper than a 4 to 1 side slope to have a barrier. The newer standards call for a 3 to 1 side slope without a barrier, but 3 to 1 to 4 to 1 is considered the critical region in which the vehicle must go to the bottom. 4 to 1, they can redirect the vehicle. This is the tests that were conducted on drainage structure to determine the opening that might be traversed by a vehicle. Here you see the Honda Civic with the 5-foot test pit that was constructed in order to attempt to measure the performance characteristics of various size openings. The 5-foot pit was considered to be sufficiently long for any testing that we might wish to do. The basic test at this angle is 90 degrees with a 20-degree opening and a 20 mile per hour, that was 20 miles per hour and a 24-inch opening. And the Honda Civic sailed over it with no problem at all. No tendency to be unstable, no problem with the wheel snagging in the hole. So the pit was increased to 30 inches in the test run again. 30-inch opening, 0 angle of attack, head on, 20 miles an hour, and the Honda gets over it again with relative ease. No real problems in jumping over a hole of 30 inches. So one more try with a 36-inch hole, but this time at 30 miles an hour, because we weren't all that sure of our testing procedure. And 30 miles an hour, 36-inch opening at 30 miles an hour. And the performance again was very good. This is one of the prototype concepts that were included in the test sequence. These are 16-inch openings between 2.5-inch pipes. The 22-inch Honda wheel then might have a tendency to fall in, so we drove it across at 10 miles an hour to see if a serious problem would occur. What if the vehicle were just barely rolling? And you can see that it gets across with relative ease, really no problem in traversing the opening as much as 16 inches. Now that compares to the existing FHWA standard of 12 inches. So one more try, this time with two 30-inch openings, one pipe down the middle. The idea is to see if the vehicle can traverse without losing control 2 30-inch openings. Again, the Honda did a remarkably good job of getting across the system. While there's a bounce to the axles, there's very little transmission of that motion to the passenger compartment itself. This is the large car, which was kind of an afterthought. We had not intended to run the large car simply because we didn't think it would be a serious problem. But to just verify the results that we were getting, we thought we should have the 4,500-pound test vehicle. So this is the 4,500-pound test vehicle at very low speed, and low speed is the more critical speed. And notice that the action of the vehicle is a good deal more pronounced with the heavy vehicle than it is with the Honda. The difference being the suspension system beneath the vehicle. The softer suspension system of the larger vehicle dropped more quickly, and that in turn created or translated more action to the vehicle compartment itself. Taking these ideas and translating them to prototypes, this is a roadside pipe 30 inches in diameter, cut to match the side slope with an apron around it for erosion protection. We're going to run the vehicles across this 30-inch opening with 90-degree attack angle to see what effects it might have if there's a serious problem damage-wise. And this time the 4,500-pound vehicle goes across with virtually no problem at all at low speed. And low speed is typically the more critical case. This is looking down the throat of the system, and the flash is simply film coordination. You can see the wheel drops very quickly, and the tire does impact the rim on the backside, and there is a loss of tire pressure in one of the tires. But all in all, the driver came across relatively unscathed in the impact. Very modest damage occurs to the vehicle. This is the same basic test with the Honda Civic, again to determine the difference in vehicle size on performance. So 30-inch pipe shaped to the side slope on a 5-to-1 side slope, and the Honda Civic is to go across at 90 degrees. No erratic action, no major problem with the vehicle traversal, relatively safe configuration. So the side slope for up to 30-inch pipes shaped to the side slope seems to be relatively safe. This substantially eliminates the problem of debris blockage of the drainage inlet, which has been a significant problem with some of the grates that we've been using for the last several years. The Honda again jumps over it pretty cleanly with actually less problem than the larger vehicle. This is the prototype concept for the box culvert with one modification. The hydraulics people indicated they had to have a 1-foot section at the end, and in spite of the fact that the safety people told them it was unsafe, they insisted on testing it. So therefore you will see several tests going across the surface of the grate system, and then one coming over that end section, the stand-up end section. We're coming across at 90 degrees with the intent of seeing if the vehicle can survive the impacts of a 30-inch pipe spacing on a relatively extended opening. The speed is approximately 30 miles an hour. This is looking down from the top, and you see the action of the axles as it comes across the system, and by far the most violent action is the rear axle in the process of traversing across the 30-inch openings of the grate. Same test with the larger car, this time at about 20 miles an hour, and the project requirement was to try to steer back toward the roadway to see if that would have any effect on the traversal pattern. So you notice they've already started counter steering at this point. The vehicle does clear across, but the rim is bent, and pretty obviously the tires are flattened in the process of the traversal. While that's not the most desirable way to get across, it is certainly safe. And that's the intent, to get away from the stand-up head wall, concrete that we've used for so long, and match the box culvert to the side slope with a grate with large enough openings to provide for passage of most debris, solve the hydraulics problem, and still be survivable by the motorist. This is the high-speed test of the drop-off situation at the end, just to prove conclusively that it can't work. And it does so very dramatically. As the vehicle drops off of that end, it simply rotates, and when the wheels impact the soil in the ditch, it's tripped and rolled. The final prototype of this design extended the apron out in the ditch line and used pipe extensions down to the flow line rather than the stand-up cross member, and so the horizontal member that you saw in this example does not exist in the final design. A little bit larger pipe is required because of the extra span. Instead of 2.5-inch Schedule 30 pipe, it is 3-inch Schedule 30 pipe, and otherwise it's anchored directly to the concrete at the flow line, and minimal problems of maintenance are expected to occur. This is a one high-speed run across the top with the vehicle again counter steering toward the roadway, just to ensure that we had not overlooked something in the previous test. And you can see the high-speed 60-mile-an-hour run. The vehicle just comes clear over the top of it, virtually doesn't touch the grate system at all. At this point, we have completed essentially 1 year of research, and the next problem that the drainage safety people undertook simply was what happens when a vehicle hits head-on into a driveway slope. We had done it on the computer, so here we're doing it in a live situation. This is a 4-to-1 front slope, the vehicle attacking head-on. And we're trying to look at the trajectory of the vehicle as it goes up and over a 20-foot crossover. This would be typical of freeway median crossover situation and not atypical for roadside access roadways to property. 30 miles an hour with a 4-to-1 front slope and a 5-foot high fill section. Notice the vehicle was projected about 3 feet, 2.5 to 3 feet above the berm, came down at the top of the back of the berm, and wasn't too bad a ride. A little bit rough on the end, but not really all that critical. On the other hand, 30 miles an hour is local street speed, not highway speed. This test is 35 miles an hour at 90 degrees with the same Pinto and Vega, and the Vega jumped completely over the 20-foot berm and landed on the soil. Relatively rough landing, but not unsafe. 35 miles an hour. At 40 miles per hour, the severity of the situation begins to become obvious. The Vega one more time, 40 miles an hour, up and over the 4-to-1, and notice that it flies a considerable distance this time, impacting with the front bumper and doing substantial damage to the vehicle. Notice the height of the trajectory, about 12 feet from the ground line, 6 or 7 feet above the top of the berm, and the bumper impacted first, causing a substantial deceleration. The computer had told us at 48 miles an hour the car would flip end over end. This is 50, and you see exactly that happened. When the bumper came down first, the vehicle tends to roll end over end. Notice the height of the trajectory again, going up nearly 9 feet higher than the berm, so 12 to 14 feet in the air. When it comes down on the front bumper, and that causes the vehicle to go into a roll mode. This concept then was carried into prototype testing, and here you see the concepts of both studies linked together. This is a 30-inch pipe going under a driveway on a 6-to-1 front slope, and the cross members have been placed on there at 30-inch centers to allow the rear vehicle wheel to ride up over the top rather than being thrown up violently by the top of the pipe. With the wheels right in the pipe, it's a rough ride, but not unsafe and critical. So therefore, we feel that with a member that's 18 inches or larger in dimension as a drainage pipe, that cross members at 30-inch centers can successfully redirect the vehicle up and over the 6-to-1 or flatter berm with a minimal problem.
This film presents an overview of a study by the Federal Highway Administration to evaluate the safety and economics of small sign supports. For comprehensive details of the study, the viewer should acquire reports noted in the film. Roadside signs are a vital part of any highway or street system. Numerous types of signs are needed to convey necessary information to motorists. Within the 50 state highway systems alone, there are more than 12 million roadside sign installations. Millions more are used within county and city jurisdictions. Small single-post installations comprise approximately 80% of all roadside signs. Costs associated with their installation and maintenance are substantial. Many installations are replaced annually due to accidents, vandalism, and normal wear. It is not uncommon for a state transportation agency to spend 10 to 15% of its annual maintenance budget on small signs. Cities and counties may even spend a larger percentage. Mr. Chuck Armstrong with the Pennsylvania Department of Transportation, Bureau of Maintenance.
Yes, Hayes, this pile represents approximately 3 or 4 months wreckage due to being struck by a car, vandalism, or any other factors that might cause it. The total number of signs that we replaced during the year run upwards of 200,000.
Mr. John Reglin, Assistant Director of Transportation for the City of Houston.
Our budget for this year is $3.3 million. At this time, it looks like we'll spend just under $400,000 for materials and labor installing and maintaining signs within the city limits. So this would be in the vicinity of 10 to 15% of our budget.
Thousands of small signs are hit every year by errant motorists. In the past, there was little concern for the hazard of small signs. The big cars we drove simply rode over them or knocked them out of the way. As the trend towards smaller, more economical vehicles continues, we can no longer ignore the hazard of small signs. These small cars hit commonly used single-post installations. A survey was conducted in the initial phase of this study with state, city, and county agencies to determine the state of the practice in small sign supports. Follow-up phone calls and personal interviews were made with selected transportation officials to fill voids in the questionnaire data. The 4 most common types of small sign supports are, in order of use, the steel flanged channel or U-post, wood post, standard steel pipe post, and square steel tube post. Shown here are field installations of the steel U-post, a support widely used by state, city, and county transportation agencies. In some cases, 2 U-posts are bolted together to form a larger support, and these are referred to as piggyback or back-to-back U-posts. Typically, the U-post is driven in the ground either by hand or by powered equipment. Aluminum posts, similar in shape to steel U-posts, are also used to a limited degree. This is a Type X aluminum post. A relatively new concept designed for use with steel U-posts consists of a signpost-stub post combination with a bolted base assembly. Installation is accomplished by first driving a stub in the ground. Then the signpost with sign attached is bolted to the stub. This system has an advantage over full-length U-posts in that it can be installed from ground level and requires no special equipment. Wood posts are widely used by state transportation agencies. Douglas fir and southern pine are the most common types of wood used. Wood posts are typically placed in a drilled hole, and excavated soil is then tamped around the post for embedment. In some cases, wood posts are mounted in concrete footings. In In this case, a metal sleeve is used with the concrete footing to facilitate removal of the stub if the post is knocked down. Holes at the base of the post reduce the impact force when the sign is struck by a vehicle. Standard steel pipe is used by several states and many city and county agencies. Aluminum pipe is also used, but to a smaller extent. Pipe posts are sometimes placed in a drilled hole. An excavated soil is tamped around the pipe for embedment. Pipe posts are also driven, and in some cases are placed in concrete footings. When embedded in the soil, vanes are sometimes welded to the base of the pipe for torsional or twisting resistance. The breakaway slip base is also used with pipe posts, and in some cases with square or rectangular tube posts. The triangular slip base will break away irrespective of the direction of impact, while the rectangular slip base is primarily a unidirectional device. Another method which has been successfully used to weaken the pipe post during impact is the so-called pipe collar design. A short pipe stub is embedded in a concrete footing with a threaded pipe collar attached. The threaded base of the signpost is then attached to the collar for installation. The system is designed to break at the juncture of the collar and the signpost. Square or rectangular steel tubing has gained wide acceptance in recent years as a small sign support. It is widely used by state, city, and county agencies. Installation is typically accomplished by first driving a stub post, which is larger in size than the signpost. The signpost is then inserted in the stub and held with a fastener. For smaller post sizes, a sleeve is inserted along and on the outside of the stub to provide greater strength at the base of the post. Vehicle impacts cause the signpost to bend and or break at the top of the stub. The second phase of the study involved a full-scale crash test program to evaluate the impact hazard of widely used small sign supports and promising new concepts. All installations tested were the single signpost type. In accordance with current guidelines, compact automobiles weighing approximately 2,250 pounds were used as test vehicles. The posts were impacted either 15 inches to the left or right of the center of the front bumper. Each test vehicle was instrumented for measuring deceleration during impact. Soil at the test site conformed to recommended standards for crash tests. With regard to safety, change in vehicle momentum during impact is the primary factor used to evaluate the impact behavior of a signpost. The American Association of State Highway and Transportation Officials specification states that the change in momentum for a 2,250-pound automobile should not exceed 1,100 pound-seconds, but desirably does not exceed 750 pound-seconds. This means that the change in velocity during impact should not exceed 10.7 miles per hour, but desirably does not exceed 7.3 miles per hour. Also, after impact, the panel and/or post should not penetrate into the passenger compartment, and the vehicle should remain in a stable, upright configuration. Aluminum sign panels were used in each test. A 24 by 30-inch panel was used with the smaller posts, and a 36 by 48-inch panel was used with the larger posts. The bottom of the panel was approximately 6 feet above ground in each test. The first series of tests involved full-length steel U-posts. This is a 3-pound per foot rib back post driven 3.5 feet into the soil. It is rolled from billet steel, having relatively high strength and toughness. Tests at 21 miles per hour and 61 miles per hour were conducted. This is the 61 mile per hour test. Note that the post momentarily wraps around the hood of the car, producing significant impact resistance. Change in momentum exceeded the desirable limit. Note that in each test shown, brakes were locked when the vehicle was approximately 50 feet beyond the impact point. In most cases, this caused the vehicle to spin out as it came to a stop. This test was identical to the previous test, except in this case the U-post material was rail steel, which has high strength but relatively low impact resistance. Impact speed was 64 miles per hour. Note that the post fractures upon impact, and as a consequence, the post and panel rotate down into the windshield. Change in vehicle momentum was well below the desirable limit. Tests were conducted on 2 3-pound per foot steel U-posts bolted together to form a back-to-back section. The posts were embedded 4 feet in the soil. This is a 61 mile per hour impact with the rib back billet steel design. Change in momentum was well in excess of the limiting value. As a consequence of the previous test, an experimental billet steel U-post was produced by a manufacturer of this design. Material properties were changed to reduce the impact resistance. This is a 58 mile per hour impact with the experimental back-to-back post. Much better impact behavior was observed, and the change in momentum was below the desirable limit. Damage to the vehicle was considerably less than in the previous test. This is a 63 mile per hour test of a rail steel back-to-back design. Impact behavior of the posts was similar to the experimental billet steel posts. Change in momentum was below the desirable limit. However, the post and panel were carried along with the car for a distance before dropping in front of the vehicle. This tripped the vehicle, and it rolled. Probability of such an occurrence is unknown, but believed to be small. Note that the panel dug into the soil and tripped the vehicle. Tests of a bolted signpost stub support system utilizing steel U-posts have been conducted by industry. This is a 3-pound per foot rail steel post and stub, and the stub was driven approximately 3 feet. Impact speed was 60 miles per hour. Change in momentum was well below the desirable limit. Other tests have been conducted to evaluate the behavior of the system for low-speed impacts, as well as impacts from the side and rear of the installation. Change in momentum was well below the desirable limit in each case. Subsequent to these tests, design changes were made in the bolted assembly to reduce damage to the stub. Further tests verified the improved design. Note that damaged posts can be salvaged for use as stubs on other installations. The final series of tests involving steel U-posts were conducted on a braced leg design. 2 2-pound per foot posts are driven in the ground to form the support system. Tests at 20 and 61 miles per hour were conducted. This sequence shows the high-speed test. Change in momentum was below the desirable limit in this test and slightly above the desirable limit in the low-speed test. An extruded aluminum post with a cross-section similar in shape to the back-to-back steel U-post was evaluated. This is a Type 3X post, whose strength is similar to that of the 3-pound per foot steel U-post. Impact speed was 64 miles per hour. Note that the post wraps around the vehicle, fractures, and remains with the vehicle. Change in momentum was well below the desirable limit. These posts can be recycled and have a substantial salvage value. Low and high-speed tests were conducted on a 4x4-inch wood post, and a low-speed impact was conducted on a 4x6-inch wood post. Grade 2 southern pine posts were used with no breakaway or weakened sections. The posts were embedded 4 feet in the soil. This is the high-speed impact with a 4x4-inch post. Change in momentum in all 3 tests was below the desirable limit. Three tests were conducted on standard steel pipe posts embedded 4 feet in the soil. An anti-twist plate was welded to the base of each pipe. No breakaway or weakened sections were used. Low and high-speed tests were conducted on a 2.5-inch diameter pipe, and a high-speed test was conducted on a 2-inch diameter pipe. This is the high-speed test with a 2.5-inch pipe. This is a high-speed impact with a 2-inch pipe. Change in momentum was less than the desirable limit. Tests were conducted to evaluate a 2.5-inch pipe with a breakaway collar design. In the first 2 tests, the system was impacted at 20 and 63 miles per hour. This sequence shows the high-speed impact. Change in momentum was less than the desirable limit. Note the stub broke just below the collar, and the entire support would have to be replaced. A minor change was made in the embedment procedure to reduce impact damage. A subsequent test at 20 miles per hour verified the improved design. Change in momentum was below the desirable limit in the 3rd test. With a change in the embedment procedure, the signpost broke just above the collar, and only the signpost would have to be replaced. The final test involved a square steel tube post. A 2.5-inch square 10-gauge post was embedded in a 3-inch square base. Impact speed was 61 miles per hour. Change in momentum was less than the desirable limit. Damaged posts in this system have salvage value since they can be used as bases for other posts. Recent crash tests of this system by industry have proven it meets current safety criteria for a variety of single post size configurations. In summary, 2 single post systems were found to be unacceptable in terms of current safety criteria. These were 2.5-inch inside diameter and larger standard steel pipe having no breakaway or weakening device, and 2 3-pound per foot and larger billet steel U-posts bolted back to back. Although a back-to-back rail steel post meets safety criteria, it is marginal at best, and a more crash-worthy system should be strongly considered. 2 systems were found to be marginal in terms of current safety criteria. By marginal is meant the change in momentum was above the desirable limit, but below the maximum limit. These were the braced leg design with 2 2-pound per foot billet steel U-posts and the 3-pound per foot full-length billet steel U-post. Single post systems which satisfied the AASHTO safety criteria included the 3-pound per foot rail steel U-post or its equivalent, the bolted base rail steel U-post system for post sizes up through 4 pounds per foot, wood posts up to 4 by 6 inch in size with no breakaway or weakening device, standard steel pipe up through 2 inches inside diameter and size with no breakaway device, standard steel pipe up through 2.5 inches inside diameter and size with the breakaway collar design, square steel tubes up through 2.5 inch by 2.5 inch 10 gauge in size, and the Type X aluminum post up through the 3X in size. Although not tested in this study, it has been proven that the slip-base breakaway design will meet required safety standards for a variety of post types and sizes. Tests have shown that this is another acceptable device which reduces impact severity. It utilizes a coupling and load concentration design which is adaptable to a variety of post types and sizes. It can be used on new installations or can be used to retrofit supports which do not meet current standards. In the final phase of the study, procedures and guidelines were developed to assist transportation officials in selecting a small sign support system. As outlined in the guidelines, each candidate system should be carefully evaluated in terms of safety, design, and economics. Regarding economics, the guidelines address the following: initial cost of system, annual cost of components, annual costs to install new systems, annual costs to restore systems damaged by errant motorists, and annual costs associated with maintenance, such as painting of posts. Careful consideration should also be given to manpower, equipment, and expertise needed to install and maintain a system. Cost effectiveness of the various systems presented is a function of a number of factors. Since many of these factors vary with time and geographic areas, it is essential that selection be based on values applicable to the given locale at the time of the analysis. As you have seen, there are a variety of ways to support a small sign, some obviously less hazardous than others. Some are simply not acceptable. Each support system has its own design characteristics and attendant costs, and it is incumbent upon those responsible for selecting sign supports to review present systems and take positive steps toward any improvements that can be made. Data and procedures developed in this study provide an objective means by which a safe and cost-effective system can be chosen. Comprehensive details of the study are presented in 4 reports, available through the Office of Development, Implementation Division, Federal Highway Administration, Washington, D.C.
This series of tests was conducted to see how barriers perform when they're down on a side slope. The test situation is a 6-to-1 side slope, and the barrier is located 6 feet from the break point. There is a 6-foot berm off of the edge of the concrete, and then a 6-foot run out to the face of the barrier. So the barrier on a 6-to-1 slope is 1 foot lower than the normal configuration. 4,500-pound vehicle, 25 degrees and 60 miles an hour, simply goes right over the top. And looking at the test situation in high speed, notice that the rail leans back, and as a result of that leaning, the wheel gets on the face of the barrier and it ramps the vehicle up and over. After this test was conducted, a follow-up test at 15 degrees and 60 miles an hour was conducted to see if redirection could be achieved for the normal impact angles. 25 degrees is an extreme angle and would not occur in normal practice very often. So therefore the question boils down to, would we have to go out and replace those barriers on a 6-to-1 slope, or are they relatively functional for normal impact angles? So this is 15 degrees and 25 miles an hour, the so-called severity test, 4,500-pound vehicle, and we do get redirection, and it was a positive redirection, but a little bit more violent than we would actually desire. We would prefer the vehicle go down the barrier face rather than being thrown back across the traffic stream. Remember, this is the severity test rather than the strength test. The strength test is redirecting the vehicle with no penetration behind the vehicle, behind the barrier. This particular test is concerned primarily with the forces on the driver. Obviously, penetration or ramping over is not desirable either. Two thoughts came out of this particular test sequence. One is that a higher barrier might be more functional down on a 6-to-1 side slope, and the other one was that a barrier that would be a little more yielding, that didn't lean with impact, might be more functional. You will see these tests coming up. Now we've moved the barrier out to 12 feet down on the side slope, or 2 feet lower than would be the normal mounting height at roadway level, and the 25-degree 60-mile-an-hour impact is to take place. The idea was the vehicle is too high when it impacts the first barrier, and therefore moving it out will cause better redirection because the vehicle would be closer to the ground. Notice that a better redirection did occur, but it became a very violent collision, and we will look at this in more detail later on. At this point you see it is snagged on the rail, and out comes the axle and wheel from the right side of the vehicle, indicating a very severe impact with the barrier. What inadvertently occurred was a 1-foot W-beam section that's designed to go at the intermediate post on the 12-foot 6 rail section was omitted, and the vehicle impacting the barrier bent the W-beam around the blockout and simply cut it in half. The vehicle then snagged on the post and rail end and ripped the undercarriage apart. This demonstrates, I think, conclusively the need for that 1-foot backup section. There you see one from adjacent post laying on the ground, but the brake point did not have that 1-foot backup section. This is a small car with the same basic setup in the 12 feet out from the brake point, or 2 feet lower than normal, 15-degree impact at 60 miles an hour. Again, a very effective redirection was achieved, indicating that barriers down on a 6-to-1 slope are not particularly critical in the normal operating situation, but we should not be installing them down on that slope in the future. We would prefer to keep them up at the 10-to-1 or flatter terrain situation, thereby satisfying both the strength, the 60 miles an hour, 25-degree criteria, as well as the severity, 15 degrees and 60 mile an hour criteria. This shows you the relative damage to the rail for the lighter vehicles is very modest as compared to the previous damage from the heavier vehicles. Again, the vehicle trajectory after impact was rather extensive, even though the damage to the vehicle was relatively minor. The trajectory problem is a far greater concern than the damage to the vehicle itself. This is the other idea that we had. If the rail was leaning and causing the vehicle to ramp over the top, then one method of correcting that would be to go to a flexible system. In this case, the cable J-hook roadside barrier. In the concept, the cables are located at 30, 27, and 24 inches above the ground, respectively. The idea is the cable should intermesh with the sheet metal on the side of the vehicle and create redirection. 60 miles an hour, 25 degrees, and notice that we got good redirection down to the time that it impacted the end anchorage. This is not an operational end anchorage, but is an experimental test facility, and the end anchorage was one that provided good tension in the cable. Notice that only one of the 3 cables engaged the vehicle. The other 2 went under the vehicle. But only one cable was necessary to provide the redirection. The problem is where to put the cable, so therefore we have to put 3 cables on at 3 different heights to provide for the range of vehicles that are in the traffic stream. This is an operational barrier and is not a problem from the standpoint of installing it, provided it has J-hooks and provided the 3 cable system is used at 30, 27, and 24 inches above the ground. This illustrates the fundamental problem that goes with the cable barrier system, and that is extensive damage as a result of the impact. So several hundred feet of rail will be replaced as compared to, say, 50 to 100 feet that might be damaged in a W-beam impact. So the maintenance costs are considerably higher. This particular instance is a smaller vehicle, 2,250-pound vehicle, impacting the cable system at 60 miles an hour and 15 degrees. Notice one of the cables goes over the hood, but the intermediate one snags the sheet metal and redirects the vehicle, so that's not a major concern. The vehicle is redirected back along the rail, and notice it tends to come back to the rail, and that in turn minimizes the trajectory problem that was so pronounced in the W-beam testing. Again, the end anchorage that the vehicle impacted is not a standard end anchorage. It is for the test installation only and would not be something that you would see in the field. In the presentation a bit earlier, you saw the recommended end treatment for the cable barrier system. Again, the damage to the vehicle is very moderate. The damage to the barrier is rather extensive, and the maintenance cost is the primary reason for not using the cable barrier in general. The main purpose of utilizing it is to allow the snow to blow through in the areas where snow accumulation is a problem. This is the Thri-beam barrier, which is mounted at 32 inches above the terrain and 6 feet off of the basic brake. The impact will be with a 4,500-pound vehicle running 60 miles an hour and with an angle of 25 degrees to the barrier. The idea of the taller barrier would intercept the vehicle more effectively and redirect the vehicle was proven to be ineffective. Raising the height didn't solve the problem. Again, if you watch the right front wheel, the barrier leans back, the tire gets on it, and the vehicle simply ramps right up and over it. So metal beam barriers must be on very flat terrain in order to be effective for the strength test, the 25-degree, 60-mile-an-hour test. The locations that exist on 6-to-1 or flatter are relatively safe. We don't recommend pulling and replacement, but for steeper slopes, it would be appropriate to replace those barriers on the slope as quickly as it's practical to do so. This shows you the damage that has occurred and the ramping action that occurred, and that little bit of lean is all that's necessary to get the vehicle up and over the top of the barrier.
This is the original stand-up end that was common in the 50s and 60s, and it simply penetrated through the vehicle on frontal impact. The first attempt at a solution to this particular problem was the Texas twist. And as you can see from the film, the Texas twist was a satisfactory solution to the penetration problem, but resulted in some cases in a rollover, as the film illustrates. Note particularly that the front wheel passes directly over the second post, and as the rail fails to come down, the vehicle right side is elevated and rollover occurs. The VCT was designed to try to eliminate this particular problem. The concept was a relatively weak beam and supported tensile strength-wise by a cable coming down from the rail through the first post. On frontal impact, the post would break, the cable would be released, and the rail would buckle in front of the vehicle as a crash cushion. Here you see that action. Low speed impact with a small car, the post does break away satisfactorily, and the W-beam buckles behind the impacting vehicle. Damage to the vehicle was moderate. This is a high-speed crash with a large vehicle with the same system. And notice that rollover does occur. The force required to buckle the rail, plus the leaning action of the second post, resulted in the rollover very similar to the Texas twist design. Modifications of the system were made to include a hole in the second post, and the washers were removed on the second through the seventh post to eliminate the problem associated with the rollover that was observed before. After the basic design was worked out, several high-speed crash tests were conducted with both steel post and wood post systems to determine the behavior of the end and high-speed impacts. And here you see the basic action of one such crash test in which the front quarter panel and door were ripped off of the vehicle as impact occurred. While undesirable, this impact was considered to be marginally safe. Much safer than penetration of the passenger compartment by the stand-up rail, as we saw earlier. Damage to the vehicle was very severe, and the decelerations on the passengers and occupants were marginal. Variations in the system were then attempted to determine if we could eliminate some of the problems associated with it. And here we see a second test. The situation is a little less severe than had previously been noted. Again, the peeling action does take place. The right quarter panel is taken off, but the door remains intact. A little more rolling action than was observed in the previous test. Following this series of tests, the BCT was considered to be relatively safe and was widely used on the highway system. With the advent of the small car, the question of the suitability of the BCT was of grave concern, and a series of tests were conducted in 1980 to determine how safe the end treatment would be with a 2,200-pound class vehicle. Here you see the head-on crash. The end treatment does fracture, and the tripping action takes place as a secondary impact of the rail end with the rear axle of the vehicle. The passenger in this case was not strapped in, the driver was, and you will note that the passenger's head went through the windshield. Here's the shot from the side, and the tripping action is well illustrated. Again, a little different angle of the collision. The first post does break, The second post breaks and yields, the secondary buckling occurs, impact occurs with the rear axle, tripping the vehicle, and rollover occurs. Here's the side in view again, and the buckling action, braking action is very clearly depicted. Head on, notice the buckling action that takes place, the post yield, the vehicle rotates, secondary impact occurs, the rear axle and tripping action is initiated. Had this been a large car, that secondary impact would very probably occur with the rear door, and penetration of the passenger compartment would have resulted. This action has indeed been noted in several field installations across the country, notably in the state of Indiana. Overhead view, buckling occurs, impact with the first buckle section, then the second one, which is the stiff one, and the rotation, rollover action is initiated. Following this series of tests, a full-scale program was initiated to try to come up with a retrofit for the VCT. To date, no satisfactory system has been reported from that research. We are looking forward to those data becoming available in the near future.
The necessity for creating both safer automobiles and more forgiving highways became critical when highway fatalities reached the 50,000 mark in 1965. 35 to 40% of those fatalities occurred when a single vehicle ran off the road and collided with a fixed roadside obstacle, such as a bridge pier, a structure at an exit ramp, an unprotected guardrail end, or an unshielded pole or sign support. Once aware of the problem, engineers were quick to develop effective solutions. Where hazards could not be removed, they were made to break away or were shielded with a positive barrier. When it was not possible to eliminate or otherwise treat a hazard, another approach was necessary. This led to the development in the late 1960s of highway crash cushions. Crash cushions are impact-absorbing devices which allow motorists to drive away from otherwise fatal accidents. The earliest crash cushions, or impact attenuators, consisted of rows of metal drums, specially weakened to crush on impact. Another type, an array of sand-filled frangible plastic barrels, was designed to dissipate the energy of an impacting vehicle through momentum transfer as the sand was displaced. Many of these early systems continue to provide life-saving service. Still another variation employed clusters of water-filled vinyl tubes which dissipated impact energy in a controlled fashion as water was forced out through the top of each tube. The principle of water-filled tubes was expanded to become the hydro-cell sandwich system. On impact, kinetic energy is gradually dissipated through the release of water in the tubes and the compression of the hydro crash cushion. This system is particularly useful in protecting wide hazards at gores, exit ramps, and bifurcations. The hydro system is also effective in safely redirecting vehicles which strike the unit from the side. Since the system is reusable, maintenance and repositioning are simple and inexpensive. Only the water expended in the crash must be replaced. The many narrow obstacles which exist along the nation's roads present quite a different problem. In order to shield these hazards, a specially designed system called the Guardrail Energy Absorbing Terminal, or GRATE, was developed. The GRATE system employs an expendable energy-absorbing cartridge in a metal framework of triple corrugated guardrail sections. When the unit is struck, its soft plastic nose molds to the front of the impacting vehicle, and the unit telescopes inward as the energy-absorbing cartridges are crushed. Expended cartridges are quickly replaced with new ones, and the unit is brought back into service. The first GRATE cartridges consisted of vermiculite concrete cells placed in a removable container. As the cells were crushed, the kinetic energy of the vehicle was converted into work, resulting in a controlled, safe stop. In response to the growing number of smaller cars with extra sensitivity to crashes, a new energy-absorbing medium has been developed. Called hex foam, the new medium consists of a honeycomb matrix of hexagon-shaped cells filled with polyurethane foam. Layers of hex foam are encased in a polyethylene shell. In addition to solving the problem of shielding narrow roadside hazards, the GRATE system has been modified to offer protection in highway construction and maintenance zones. The construction zone GRATE has been adapted so that it is portable and can be moved along as construction progresses. Still another development has resulted from the need for better safety for workers and motorists in construction and maintenance zones. The truck-mounted attenuator, or TMA, employs the lightweight hex foam cell as its energy-absorbing medium. Attached to a shadow truck, the TMA shields workers from passing traffic. Since the TMA is able to bring an errant vehicle to a controlled, safe stop, both the motorist and the highway worker are protected by its life-saving presence. Whereas crash cushions are effective in dissipating the energy of impacting vehicles, other devices have been developed to aid motorists in avoiding hazards in restricted traffic areas. Portable electronic changeable message signs are being used throughout the United States to provide motorists with clear, bright traffic advisory and safety information. More forgiving highways are being achieved through continuing research programs, products from innovative companies such as energy absorption systems, and the willingness of highway engineers to adapt new techniques in the spirit of improving highway safety.
This is a live scene in Los Angeles area. You see traffic approaching at the top, and below is the crash cushion. Notice the vehicle impacted it and spun to the side, but the driver was alert enough to turn on the flashers and therefore not seriously injured. These are live, actual crash cushion hits filmed at night on video and then transferred to 16mm film and then back to video, so therefore we have a problem. The vehicle swerving to the left just barely caught the nose of the crash cushion. And that, of course, is a fairly typical impact for that type of situation. Here's one coming right down between the paint lines, holding a good steady line until right at the end, and then veered off to the right, just barely grazing the side of the crash cushion. Crash cushion, vehicle moving at the top as you see, and the vehicle comes in and snags substantially on the back of the crash cushion. That snagging problem we will talk about in greater detail later, but the basic problem exists at every crash cushion of the kinetic energy type or combined energy type. Head on, right between the paint lines, into a steel drum crash cushion. Notice one of the drums was actually knocked out into the roadway. The vehicle driver was still alert enough to be putting on the brakes, so therefore not severely injured. Out of some 100 sequences that were filmed in this study, there was one fatality, which we will show you in a little while. Right between the paint lines again, coming right down to the crash cushion and just nudging it. This particular type of hit is most troublesome because it puts slack in the cables and is a problem. Now watch the center at the top as the truck right now makes a lane change and hits into the side of the hydrocell. Didn't quite complete his lane change before he got across the roadway, and as a result slapped into the side of the hydrocell. Head on with a steel drum system again. This is a Volkswagen at about 55 miles an hour. The driver was not seriously injured, even though there are people, as you will see in a moment, coming out to help. The driver was not seriously injured in the impact and was able to drive the vehicle away. This again is a Karmann Ghia at about 60 miles an hour and head on into the crash cushion. Again, no major injuries were sustained. Minor injuries, but nothing major. Watch the lane on the left side of the median. The truck goes by and here comes the lane change. Primary impact and two secondary impacts. This is the incident in which a fatality occurred, and it was the driver in the second vehicle in the impact sequence that was in between two vehicles that was killed. But again, the last minute lane change, forcing the driver into the crash cushion, was the basic problem.
A series of full-scale crash tests of bridge rails and guardrail to bridge transitions was conducted in 1984. The tests were generally conducted at the high side of the standard testing criteria. You will see that the results were severe and disturbing. These results indicate that the majority of existing bridge rails and transitions are structurally and/or functionally inadequate. These tests further demonstrate that performance standards for roadside appurtenances should be established and that testing should be conducted to assure that an approved design will function adequately. This test is on a type of concrete bridge rail. An open joint in a post in this concrete railing allows the test vehicle to snag on an undeflected railing end. Our test vehicle weighs 4,600 pounds, is traveling at 60 miles per hour, and impacts at 25 degrees. Here we see where the test vehicle hit the railing, then slid along the rail until it snagged on the undeflected end of the next open joint. This railing is undesirable from a safety standpoint. If it had met bridge specification requirements for structural continuity, acceptable redirection might have occurred. Now we look at a galvanized steel railing. The 42-inch high railing meets the AASHTO bridge specifications. The 4,700-pound car is moving at 60 miles per hour at a 25-degree angle to the railing. Watch how the open section of the rail at hood height results in the hood snagging on the post and being driven through the windshield into the passenger compartment. Designs similar to this aluminum railing are popular in some states. The 4,700-pound test car impacts the railing at 25 degrees and 60 miles per hour. This fourth bridge rail is similar to the previous one. It does not meet AASHTO specifications because the lower rail is 4 1/2 inches too high. Here, the 1,950-pound test vehicle is traveling at 60 miles per hour and strikes at 15 degrees. Upon impact, snagging of the wheels and sheet metal on the post occurs due to this high rail, causing the car to yaw until it rolls over. This tubular tri-beam railing successfully redirects our 1,900-pound test car moving at 60 miles per hour and a 20-degree angle. The bridge rail in this test consists of a W-beam backed up by 2 box beams. The test vehicle weighs 4,500 pounds, is traveling at 60 miles per hour, and impacts at 20 degrees. Upon collision, the posts break away, minimizing the potential for snagging. But more importantly, the tensile continuity of this rail makes this system work. The bridge railing in this test is the experimental CERB self-restoring barrier system. The 4,800-pound car is traveling at 60 miles per hour at a 25-degree angle and is successfully redirected. Note the tilting lever support arms that allow the barrier face to move up during impact and then return to its original position. This safety-shaped concrete barrier has an aluminum rail bolted on top. The height of the concrete parapet is 27 inches and the aluminum rail is 12 inches high. Our 4,600-pound test vehicle will strike the barrier at 60 miles per hour and 25 degrees. The vehicle is successfully redirected. Snagging could have occurred had it not been for the vehicle roll caused by the barrier face shape sending the hood over the top of the railing. This test had a small car impact a typical concrete safety-shaped barrier. The test car weighed 1,900 pounds, was moving at 60 miles per hour, and struck the barrier at 20 degrees. Even though the car became airborne, the results are considered a success. This is a test of the aluminum industry's answer to the problems encountered with the first of the aluminum railings shown earlier. Although modification of the base plate and some connection details substantially strengthen the post over the earlier version, it is still below the specification strength requirements. Our test vehicle strikes the rail at 60 miles per hour and 25 degrees. We have successful redirection. Despite two of the posts breaking away, continuity of the rail allowed this system to perform satisfactorily. These last two crash tests are of typical transitions from guardrail to bridge parapets. The test conditions in both tests were the same. Note that there is no offset between the concrete wall and the W-beam rail. The test vehicle weighs 4,600 pounds and strikes the rail at 60 miles per hour at an angle of 25 degrees. The guardrail deflects, forming a pocket which guides the test vehicle into the concrete barrier end, resulting in a very violent collision. This last test is a retrofit of the previous transition design. Two more posts have been added, so now the first 4 posts from the concrete barrier are spaced at 1 foot 6 inches, thereby stiffening the transition. Also, a W-beam rub rail, 12.5 feet long, was added and tucked behind the post. Again, we have a 4,600 pound car striking the rail at 60 miles per hour and at a 25-degree angle. While the results are considered a success, note how the W-beam deformed at the end of the parapet and how the concrete parapet cracked.
Safe highways are something everyone appreciates. However, the definition of safe as being free from harm or risk is simplistic and misleading. Nothing is absolutely free from harm or risk. There are degrees of risk, and there are degrees of safety. In our mobile society, most of our citizens take the risk daily of traveling on our system of roadways. This risk has a fatal ending for nearly 50,000 people annually. A high percentage of these lost lives and serious injuries are the result of single vehicles running off the road. For the occupants of these out-of-control vehicles, the risk is a function of what is adjacent to the road. If the area is traversable, the driver may regain control with no injury or vehicle damage. If the driver loses control near a bridge, the room to regain vehicle control is restricted and a collision is likely to happen. On a per-mile basis, the fatal accident rate for bridges is 15 times that of the typical roadway. For this reason, bridges are prime candidates for safety improvements. There are approximately 600,000 bridges in the United States. Together, they have a total length which exceeds 13,000 miles. More than 75% of these bridges were constructed prior to 1965, when a major change was made in the AASHTO bridge railing specification. Geometric requirements for railings also have been upgraded continually to improve the vehicle barrier interface. Most railings designed to previous and current criteria have not been crash tested. Some are known to have deficiencies. Bridge rail upgrading is part of an overall safety improvement strategy and can be considered as part of reconstruction or rehabilitation projects. In 1979, over 700 fatalities were attributed to vehicles crossing a bridge. Accident statistics indicate that injury severities increase significantly when vehicles penetrate through or vault over bridge railings. Deficient bridge railing systems can be identified from adverse accident experience. Common railing deficiencies include insufficient strength resulting in penetration, beam post deflection incompatibility resulting in wheel snagging, and curb safety walks which may cause vaulting. Besides low initial and maintenance costs, characteristics of a satisfactory bridge railing include forgiving redirection for occupants in a wide range of vehicles, including the growing number of small cars, adequate strength and geometry, beam and post deflection compatibility, and railings compatible with curbs and walks. A comprehensive survey conducted for the Federal Highway Administration in the mid-1970s identified 3 bridge railing categories as prime retrofit candidates. The first retrofit category consists of a metal railing system installed on a flush deck or low curb less than 6 inches high. The second retrofit category is a concrete baluster or parapet, with or without metal railings on top. Deficiencies noted in these systems include lack of adequate strength and wheel snagging at railing openings. The third category concerns bridges with a metal rail or concrete parapet on a high curb or walk. 1 to 3 rails may be installed on the parapet. This railing category is further defined as narrow walks less than 2 feet wide and wide walks greater than 2 feet. The raised walkways have caused vehicle vaulting. Presently, there are a number of upgrading design alternatives. Single thry beams were evaluated by New York State for effectiveness in providing continuity across undesirable open joints of a flush deck metal railing system. A box beam design also has been tested by New York for upgrading this railing. These retrofitted railings have been evaluated for full-size car containment. One upgraded system was tested for the baluster category, a tubular tri-beam mounted on deformable spacers. This retrofit distributes impact forces over a large area as the spacers deform, thus reducing vehicle occupant injury potential while increasing the capacity of an existing railing. The 20-inch deep tri-beam provides geometric compatibility with a wide range of vehicles. A standard full-size car test was conducted on the baluster system. Fracturing of the railing and posts occurred. The car was smoothly redirected by the upgraded system with no damage to the baluster railing. Crash tests also provide a comparison of the existing and retrofitted railing performance with a subcompact vehicle. The upgraded system in the narrow walk category had a 10-inch high walk that was 16 inches wide. As reported from the field, vehicles have vaulted over or through the metal railing on top of the parapet. Two baseline crash tests were conducted on the existing design. In the full-size car test, the vehicle was contained and redirected. However, there was considerable damage to the system. The standard subcompact test resulted in vehicle redirection, although some wheel snagging occurred at one of the metal posts. Three different retrofit designs were crash tested for the narrow walk category. The rigid aluminum retrofit system for this category features a spacer which distributes the loads from attached beams to the parapet. The beams are installed in line with the face of the curb, thus reducing the possibility of vehicle vaulting. The full-size car test with the aluminum retrofit resulted in smooth redirection with no significant barrier damage. Some sheet metal snagging occurred at one post. The subcompact car was driven from the scene after the test. A concrete beam installed on top of the safety walk provided another retrofit alternative. This upgraded system resembles a shaped concrete parapet. The additional dead load should be considered. A shallow 12-degree angle test was conducted with a full-size sedan. A subcompact test of the same system. A tubular tri-beam system with crushable tubes was installed with the narrow walk system. The beam face was in line with the curb. The subcompact test of the tubular tri-beam system resulted in smooth redirection. A full-size car test resulted in containment and redirection. Two crushable tubes were compressed, and there was no damage to the existing parapet. Tests of the tubular retrofit with heavy buses resulted in tripping of the vehicles at the rigid walk face when the beam deflected. This tripping caused the buses to roll on their side after 60 miles per hour, 15-degree angle impacts. An improved retrofit design for heavy vehicles was developed by moving the beam out 3 inches and up 6 inches. Subsequent crash tests with a 40,000-pound intercity bus and an 1,800-pound mini-compact at 60 miles per hour and a 15-degree angle produced desired results. The system selected for upgrading the wide walk category featured a 9-inch high by 5-foot wide safety walk. The steel panel type railing primarily functioned as a pedestrian railing. The baseline test of the existing system was conducted with a full-size car. The vehicle was launched over the walk and went through the railing until it contacted the downstream concrete end post. The upgraded system featured specially designed posts mounted near the traffic side of the walk. A tubular tri-beam was connected to the posts in line with the curve face of the walk. The subcompact test resulted in smooth redirection. Vehicle damage was minimal. The full-size car test illustrates the flexibility of the tubular tri-beam in redirecting the vehicle energy. The specially designed posts required no costly deck damage repair after this severe impact. Spectacular accidents have occurred at curved off-ramp structures. Concrete safety shapes and tubular tri-beam upgraded systems have been proved effective in off-ramp collisions for vehicles ranging from a 20,000-pound school bus to a mini compact car. Trucks, buses, and cars have caused collapse of through truss spans by impacting critical truss members. Through truss bridges require a rigid railing that limits large vehicle roll. A tubular tri-beam railing system with a secondary 5-foot high railing was successful in excluding from the truss member zone a 20,000-pound bus impacting at 55 miles per hour and 15 degrees. Metal safety shapes have been installed on existing bridges which could not accommodate the dead weight of concrete safety-shaped retrofits. Injuries are more severe in bridge end accidents than in bridge rail accidents. This is attributed to the incompatibility of conventional approach guardrail with traditional rigid bridge railing systems. Most of the upgrading accomplished to date has involved the physical attachment of the approach guardrail to the bridge parapet. The post spacing near the bridge is usually reduced for stiffness transition. A recent study by the state of California identified bridge approach upgrading as one of the most cost-effective safety improvements possible. Development of the retrofit systems in the FHWA upgrading project included full-size car test evaluation of bridge approach designs. The beam elements used in the bridge railing upgrading were extended beyond the structure and transitioned to a conventional approach guardrail system. The flush deck railing upgrade by New York featured a tri-beam bridge approach railing. The approach system was proved compatible with the upgraded bridge railing. For the parapet approach, the tubular tri-beam was carried one post span beyond the bridge and then spliced to a single tri-beam element. The vehicle was smoothly redirected. The narrow walk aluminum retrofit used the same bridge approach beams across the structure. Redirection was accomplished, although wheel snagging at the exposed walk end was sufficient to strip the wheel from the test vehicle. The tubular tri-beam retrofit for the narrow walk approach was extended 2 spans beyond the bridge end and connected to a single tri-beam. The bridge approach test resulted in successful redirection of the vehicle, although the parapet end fractured and significant contact with the exposed curb end resulted. This exposed end should be tapered to grade or flared to minimize snagging potential. The tubular thri-beam was extended beyond the wide walk structure and spliced to a single thri-beam. Results of the test were successful. There is a need to upgrade obsolete bridge railings. Accident experience with a given railing system can assist in identifying this need. Approach railings must be compatible with the bridge railing if the bridge end problem is to be improved. Transition designs have been developed for most of the upgraded systems discussed. There are a number of retrofit systems available for immediate implementation. Several states have significant numbers of tubular thri-beam upgraded projects. For research reports and further information, contact the FHWA office in your state.
This film is of a multiple mailbox system. We have 4 mailboxes sitting on a single rail supported by a single post. In single mailbox situations, the mailbox typically hits the windshield and bounces over the vehicle. But with multiple mailbox situations, the rail supporting the mailboxes is a critical concern. Here is a 60-mile-an-hour crash with a smaller vehicle. At normal speed, you don't see the seriousness of the problem, but at high speed it becomes evident. 3 of the 4 boxes go directly into the passenger compartment, with 1 going over the top. Since mailboxes must be located right at the window level, this becomes a very great concern. The methods of eliminating this particular behavior pretty much revolve around making the post system, support system, U-shaped so that the bumper impacts the rail on the front end and pushes it away from the vehicle rather than coming into the windshield as you saw in that test example. Very serious consequences. The driver obviously is in a very serious circumstance when such impacts occur. While these are relatively small numbers of incidents, they do result in several hundred fatalities a year on mailboxes across the country.